Okay, so at this point, we have introduced this idea of motion. How do we know that something is moving? We talked about one way that we can describe motion, and that's with speed. And typically, we talk about the average speed of an object. So, the total distance that an object moves divided by the total amount of time that it took the object to move that distance. And then we said, well, sometimes speed isn't enough. Sometimes it's not enough to know something's going 20 miles per hour. I also want to know the direction that the object is going. And if we add that directional component in, then we're talking about velocity. Well, now we've got another way to describe motion, and that is by talking about its acceleration. Now, I have two sons, and I know that one thing that they are always interested in growing up, they were both interested in cars, and one of them was interested in motorcycles. I didn't like that very much. But, sometimes they would talk about a certain car and they would say things like, that car can go from 0 to 100 miles per hour in so many seconds. And they really like to talk about how quickly some of the cars could go from 0 to 100 miles per hour. Well, what they were really talking about there is acceleration. They wanted to know how quickly is it getting up to a certain speed. So, acceleration measures the rate of change in velocity. The easiest way to think about acceleration is we're just talking about whether or not something is speeding up, slowing down, or changing direction. Now, if you look back at this definition, acceleration measures the rate of change in velocity. Then remember, velocity has speed as part of it, but it also has direction. So we would say that something is accelerating if it's speeding up. We would also say that something is accelerating if it's slowing down. And then we would also say that something is accelerating if it has a change in direction. And that's usually the one that some kids forget. We love this diagram, and I think that this would be a great thing to add to your scientist notebook. So here's a little person, and you notice it says I'm accelerating because I'm speeding up. Here's our skateboarder. We still call it I'm accelerating because I'm slowing down. We'll talk about acceleration in a negative direction. And finally, here is, I don't know if that's a butterfly or a bee. It says buzz buzz, so I guess it's a bee. I'm accelerating because I'm changing directions. So I think that is a great drawing to add in. You don't have to add this drawing in, but it's another way to help you remember what the word acceleration means. So a lot of you are going to be starting to learn how to drive pretty soon. Oh boy. And when you hit the gas pedal and you make the car speed up, we would consider that to be an accelerator. You will learn that there is a brake pedal, and you will certainly hit the brakes to slow down, but we still consider that to be an accelerator. And then finally, here's your steering wheel, and you will learn how to move your steering wheel to change direction. And so, even the steering wheel is considered to be an accelerator in physics. Speeding up, slowing down, changing direction, all of those are considered to be acceleration. Now, the next part gets a little tricky. All right, so here we go. The next part's a little trickier. I'll make that bigger. You definitely need to write this down, and you need to write this, and you need to draw these vectors. Now, remember, we show a vector to indicate direction, and the length of the arrow of the vector also tells us something about the magnitude of the quantity. So if I have an object And this velocity vector is simply telling me that it is going at a certain speed in a certain direction. If I'm also given an acceleration vector along with it, and we have seen this type of assessment question where they would give you these two vectors and then they would ask you, what does this tell you about the object? Well, if it is accelerating in the same direction, if it's accelerating in the same direction as the velocity, that object is speeding up. But if I have an object that is slowing down, then its acceleration vector is going the opposite way of the direction of its motion. So this is telling me I have some object, it's going in this direction at a certain speed, but there's an acceleration vector that has been placed with it, and it's going the opposite way. So this is telling me that it is having what's called negative acceleration, and that would mean that overall, this object must be slowing down. We don't know if this will work, guys, on your, I'm going to try this for you. We're not sure if this will work on your Chromebooks, but hopefully it will. So here's my little ladybug, and you can click it, and it will take you to this simulation. And we'll find out together if it will work. It might not. All right, it works on my computer, and it may work on just a regular PC. If you haven't, someone at your home has one, I just don't know that it will work on your Chromebooks. So you guys can let me know. So here's my little ladybug. And I'm going to put over here that I want it to show both the velocity vector and the acceleration vector. Now, I like to leave the motion manual. That means I'm going to drag this ladybug. If you want to, and we encourage you to go ahead and try putting it on linear and circular. Down here is like a little remote control. So if you don't want to drag the ladybug over here, you can actually just use this like a little control pad over here, okay? All right. So I want you to watch though, because what you're going to see are two vectors. You're going to see both a velocity vector and an acceleration vector. So let me see. Let's see. I'll have my ladybug go there. You see them both? And then I'll have my ladybug go there. And I'll have my ladybug come over here. Okay. And so you can literally just move it around. There's lots of different things that you can play with here. I do there. Okay. There. Velocity. Here's linear if you want to have it go there. I'll do the remote control pad. That seems to be a little easier. Go up here. But the big thing we want you to notice is that it's that combination of the velocity vector and the acceleration vector that describes the motion. Okay, the velocity tells me the speed and direction, and the acceleration vector gives me an idea of whether it's speeding up, slowing down, or changing direction. So you can just mess around with that. We're not going to have you do anything particular with it. We just were happy to show you that you've got a couple of different vectors going on there. Okay, guys, I'm back. So my Apple Watch rang. That was Miss Pearson calling me. So sorry about that. All right. So after you, just have fun with that ladybug moving around so you can watch those two vectors. We also need to talk about calculating average acceleration. So just like we can calculate the average speed of an object, we can also calculate the average acceleration. Let me show you. I think it's almost easier to look at a sample problem and then kind of see exactly what that means. So we're going to pretend we've got a roller coaster over here. All right, there it is. And at the top, right here, when that roller coaster comes around the top, because it's not still, right? So we'll pretend it's already been doing its thing over there. it's in motion. So it's in motion right here. And right at the top of that hill, its speed is 20 meters per second. That's its speed. And now, as it goes down, if you've ever been on a roller coaster or been on a sled, you know that its speed is going to get faster. And so, by the time it gets to the bottom right here of this little hill, it is going 40 meters per second. So it was going 20 meters per second here. It was already in motion as it came up. It picked up speed. It was going faster by the time it reached this point. Well, I want to know then. I see that that's a change in speed, right? It sped up. So that tells me that it was accelerating. And I want to know what the average acceleration was as it went from here to here. So here's the formula that we use, all right? To find the average acceleration of an object, we take its final velocity. What was it? How fast was it going here at the point that it ended at that we're interested in? And we subtract the velocity that it started with, and then we divide it by the amount of time it took to go from here at the top to here. So now here's our word problem. At the top of a hill, a roller coaster is moving 20 meters per second and increases in speed to 40 meters per second at the bottom of the hill. It takes 4 seconds to reach the bottom of the hill. So it's telling me that it took 4 seconds for the roller coaster, however we measured it, to go from here to here. And the question is, what is the roller coaster's acceleration? So remember now, I'm going to take its final velocity. I'm interested from this point to this point. So it was going 40 meters per second here. I subtract how fast it was going when it started, all right, at the point I'm interested in. So 40 minus 20, and it took 4 seconds, divided by 4 seconds. 40 minus 20 is 20. 20 meters per second divided by 4 seconds. Now, here's what always kids are like, what just happened? All right, 20 divided by 4 is 5. Everybody's good with that. Look at the unit. 5 meters per second squared. Or another way to say that is 5 meters per second per second. What does that mean? Well, let's look at this a different way. Okay, let's look at it this way. Here's the same exact equation. What this is saying is that every second, every 1 second, that roller coaster is going 5 meters per second faster. That's why it says seconds squared. Here's one of the seconds, and here's the other second. So 5 meters per second squared means that every second it's going 5 meters per second faster. Acceleration tells us how the speed is changing. So I made a data table for you. And so right here at the top of the hill, now this is average acceleration. So at the top of the hill, if the roller coaster is going 20 meters per second, then 1 second later, if it's going 5 meters per second faster, it would be going 25 meters per second. At the 2-second mark, it would be going 30 meters per second. At the 3-second mark, 35 meters per second. And finally, when it's at the bottom of the hill, it's going 40 meters per second. Now, again, this is average acceleration, not instantaneous acceleration. So I can do this with my data table. So again, our average acceleration is simply telling us that every second, the roller coaster is going 5 meters per second faster. Here's another example. When Sarah ran a race on a straight track, her speed changed from 3 meters per second to 6 meters per second over a time period of 3 seconds. What was her acceleration during that time? We should probably go back and add the word average acceleration. So remember, I'm interested in this particular period of time. So her final velocity was 6 meters per second minus her velocity at the start of the period I'm interested in, minus 3. And it said it took 3 seconds for her to do this. 6 minus 3 is 3 meters per second divided by 3 seconds. 3 divided by 3 is 1. And acceleration is always going to have 1 distance unit and 2 time units. So this is 1 meter per second squared. It's telling us that her average acceleration, that every meter she was going 1 meter per second faster. Now, you want to really get your head on straight for this next part, okay? Now, just like we had to learn how to analyze distance time graphs, we're also going to need to analyze speed time graphs. Now, again, guys, here's the thing. We have seen some of the released items on the TN Ready test and other standardized tests. We have a lot of experience with it. And I can tell you guys that sometimes they will label these things speed time graphs, and sometimes they'll call them velocity time graphs. But here is the first thing you've got to do. When you are given a graph of motion, you have to slow down and look and see what that graph is labeled. So for example, when I see this graph over here, I see that this is a distance time graph, just like the ones that we practiced with. This is just distance time. This is telling me some object is going at a constant speed away from where it starts. And then I know that this means the object isn't moving. And now I can see it's continuing to move away. Well, this graph is not a distance time graph. This graph is a velocity time graph. Or again, sometimes you might see a speed. Instead of the word velocity, you might see speed time graph. And it's different. The patterns are different. So here we go. On a speed time graph, I want you to notice here's speed and here's time. And really, guys, just kind of think about this. I think it helps to sort of just make up some numbers in there. Okay, so if I say that's 1 second and that's 4 seconds, and I'll make up some speeds right here. Okay, make up some speeds. Okay, I'll say this is 10 miles per hour, and that's 20. And this is 30 miles per hour. If you're not given numbers, just, make up some numbers. Put something in there to help you figure this out. Because if it's a speed time graph, I think this will make sense to you. A straight line doesn't mean something is not moving anymore. A straight line just means, look, that this object is going 30 miles per hour. See the 30? And it's at a constant speed right there. It's not changing. But again, you have to look at what the graph is, all right? On a distance time graph, a horizontal line does mean that the object isn't moving, but that's not what this is. This is a speed time graph. That's why I think the numbers help. Now I can just look and go, oh, at 1 second, it's going 30 miles per hour. At 2 seconds, it's going 30 miles per hour. At 3 seconds, it's going 30 miles per hour. At 4 seconds. And now it makes sense to me that on a speed time graph, this is simply showing a constant speed. Oh, let's see. Sorry, I'll have to get my eraser. I didn't realize that would go to the next little thing. Goodbye, 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 goodbye. Okay. All right, now on a speed time graph, again, if it helps, put numbers in there. I think it helps kids a lot. So if that's 10 miles per hour, 20, 30, 40, 50, read the graph. Read the graph, guys, okay? Now, when this was a distance time graph, we said this meant something was going at the same constant speed and that you could actually just take the slope of the line at a point and find the speed. This is not a distance time graph. This is a speed time graph. And so now this sloped line is showing me that this object is accelerating. It is actually speeding up. It is going 10 miles per hour. Now it's going 20 miles per hour, now 30, now 40, now 50. See how the numbers help? The opposite is going on down here. When the speed time graph has this nice line in this direction, this means that the object is slowing down, and we say that that is negative acceleration. It's going fast, and now it's going slower and slower and slower and slower. Okay. And I'll go up here and grab my eraser and get that out of our way again. All right, now what about if I'm comparing two moving objects at the same time? Oh, well, here we go. Let's say that you are interested in buying a car and you want a fast car. You want a fast car. You want a car that can go 0 to 100 miles per hour, 100 miles per hour, and you want it to go, oops, sorry, you want it to go that fast. You want to get from 0 to 100 in the least amount of time that you can. Well, you're going to want this car right here. This thing is going 0 to 100 really, really, really fast. That would not be my car. Here's Miss Buck's car. Miss Buck's car, I don't think it can go 100, but if it can, it takes a long, long time for Miss Buck's car to get here. So if you're comparing speed, what this means is that this dash line has a much greater acceleration. This is showing that both of these lines reach a certain speed, but the dash line does it much faster, okay? All right, now you are ready at this point. I guess I'll get rid of my 100 mile per hour up there, okay? So this is why we're having you draw all this in and write all this in. You notice your pencil is there because we definitely feel like you need to have all of the information on this slide, okay? All right. Now, we're still not done. There is a type of graph that is very commonly used to show acceleration, and these are called ticker tape diagrams or ticker tape graphs, and we have seen them appearing on some standardized tests that were released to us. So imagine that you have a car and there is a leaky engine in the car and it's dripping oil, drip, drip, drip. So as the car is traveling through town, it's got a drip, drip, drip. So the oil is dropping on the street. Well, if we looked at those oil drips, we could learn something about the motion of the car. For example, I noticed that these little oil drips are spaced perfectly evenly apart. That tells me that this car is going at a constant speed. It's not speeding up, it's not slowing down. But look at this one. The oil drips were closer together, and then the oil drips started moving farther and farther apart. Now remember, in your head, just picture that oil dripping. Well, right here, the car was going slower, so there was more opportunity for those little drips of oil to drip out. And now I notice the car must be speeding up. It's accelerating because I see there's more space between. Look at this one. Drip, 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 drip. But now look, they get closer together. This tells me the car must have been going pretty fast and now it's slowed down. That's an interesting pattern. Look at this. I assume this means the car is going very, very, very slow because lots of drips. And now it speeds up. This one's the opposite. It's going pretty fast. I don't know what that mess means. I would almost think that, did the car stop right there? Stop and you got a big puddle? And now it started speeding up again. So it's called a ticker tape diagram. And you are expected to be able to look at these and tell something about the motion of the car. Here's a short video. This gentleman he does a great job and gives you some examples and gives you some practice problems to look at as well about ticker tape motion graphs. All right, and then big summary for your notes on acceleration. These are sentence starters. If you are comfortable summarizing your notes on your own, you certainly don't have to use our sentence starters, but we give you these to give you some idea of what we expect your summary to look like. And that is acceleration.